Okay, guys, in this video, we'll look at the squeeze theorem and how we can use it and why we need it. The first question is, why would we need to use something like this? Well, whenever you have a sequence when the limit is not really clear, because you might have something that bounces around. Examples of that would be something like sine and cosine, because this is just going to be some random values that bounce between -1 and +1. Also alternating sequences with alternating signs, something like -1 to the power n, where again it's like positive, negative, positive, negative. So when that happens, but the number is bounded by something on the top in the numerator, we can use the squeeze theorem to prove convergence. So let's first of all talk about generally what does the squeeze theorem say. Basically, it involves three sequences. So let's just call one of them an, and then you have bn, and then you have cn, right? And what you need to know is, first of all, whether an is always less than or equal to bn. By the way, that does not actually has to happen for every single n, as long as it happens at infinity, basically. As long as at some point it's going to start happening, that's fine. So if for the first few terms, it doesn't actually have to. But if it does at some point, okay, for some n, let's say 100 and higher or something like that, what you can do is look at the limit of the left-hand side. So look at the limit of sequence an, and imagine that it is equal to some L, okay? Then you also look at the limit of the sequence Cn and imagine that that one also goes to the same exact number. So these two must match for squeeze theorem, otherwise it's not going to work. So if both of them are the same, then what happens is it forces the middle one that's kind of squeezed between the two, they both go to L, and it doesn't have a choice. It has to go to L, okay? It has to go to exact same limit. That's what it says. Okay, so let's see if we can apply it. And I'm going to first actually do part B because it's a little bit easier to explain. Let's look at the sequence sine n divided by n to the power 8. Now, some people may say, well, why can't you just use for example, L'Hopital's rule, because we've been using that. Well, that's not useful here because limit of the top does not exist. You can only use L'Hopital's rule when you have something like infinity over infinity or 0 over 0. But this doesn't happen because sine n is just like a wild. It's all over the place. It's between -1 and 1, but there won't be any pattern. So that's not going to help that way, okay? But what you can do is use squeeze theorem because you know that sine n is a number between -1 and +1. There is no way for it to be anything else. And that means that this guy right here is going to be greater than or equal to -1 divided by n to the power 8. Why? Because the smallest possible value for sine n is -1. But notice that the bottom we keep the same, so we're not changing that. On the right-hand side, we're going to get exactly the same thing, but it's going to be a +1. So why does this happen? Again, because the top is between -1 and 1, and then you can just divide everything by n to the power 8, which is a positive number, and it's still going to hold. Okay, so now let's use a squeeze theorem. Let's look at the limit of the left-hand side. Now, this is when you are having something like, well, n approaches infinity, right? You have something like -1 divided by infinity to the power 8. Well, infinity to the power 8 is infinity, okay? Okay, so this is infinity. What happens when you divide by infinity? Again, this is not a strict proof, okay? But I just want you to get a feel for what happens. When you divide by infinity, the answer is always 0. If the number on the top is a number, and it's not some infinity over infinity, and then you don't know what's happening. But if it's a number divided by infinity, that's always 0. What happens over here? Exact same thing happens. You've got 1 divided by some huge number, and that's also going to be 0. Okay, so that means that these two match, and both of them are equal to 0, which will force the middle guy to also go to 0. Okay, so let's go ahead and fill this out. And then we have the exact same thing on the other side. Okay, so again, we said both left-hand side and right-hand side converge to 0, which means by the squeeze theorem, the sequence has nowhere else to go, so it'll also go to 0. Okay, now let's look at one more example. So we're coming back to part A, and that one is cosine squared. And again, this thing is going to bounce all over the place, except you have to be careful because it has a square. Any square cannot be a negative number. So even if technically you can put this would be correct, but it's really kind of bad in terms of like this is not the best you can do, okay? Because cosine squared n is never going to be negative because it's a square of some number between 0 and 1. And so this is going to be between 0 and 1. It's not going to be between 1. Well, it is going to be between negative 1 and 1, but it's never going to be negative. So better to use a better bound, which is just 0. Okay? All right, so that's going to be over here. And notice how the bottom does not change. So be careful, the bottom does not change. It's got to be the same. So, because you're saying cosine squared is between 0 and 1. Now let's divide everything by 7 to the power n. Okay, so now let's take a look at the limit. Now, what you can see on the left-hand side is this is just 0 over something that is not 0. Well, that is actually equal to 0. So this limit is 0, but not only the limit, but every value is 0, okay? What about on the other side? Well, the same argument works as I was doing before. 7 to the power infinity is a huge infinity, okay? Like run to infinity like crazy. You got a really large number on the bottom. And when that happens, when you divide by a large number, you get 0. Okay, so again, the same thing happens. 0 on both sides will force the guy in the middle to also go to 0, which means that because both of these guys converge to 0, the middle guy also converges to 0.